and you should be good to go. Yes.
Okay, so good morning, good afternoon, good evening, depending on where you are. Welcome to this session on leakage and outsourced encryption, which will be chaired by me and Anand Raghunathan. My name is Leila Batina, and we are together chairing this session. So try to make sure everything goes smoothly and that all your questions and comments are also addressed. So in this session, we have 6 talks, 6 presentations. Each will take 5 minutes as in other sessions. And then there is also some time for questions, I believe also 5 minutes. So the first talk is on random probing security, verification, composition, expansion, and new constructions by a number of co-authors, which I won't read them all, but Abdul Rahman Taleb will present the talk. The floor is yours.
Yes. Hi, everybody. Are you seeing the slides? Okay. So,
yes, we are.
I will be presenting our work about the random probing security of masking schemes against side channel attacks. So usually when algorithms are implemented on embedded devices, they become vulnerable to side channel analysis, where an adversary can deduce information on the secret from measurements such as power consumption, for example. And so to protect implementations, one of the most popular countermeasures is the masking scheme. The idea is to split a sensitive variable into n values, where all the values except for the last one are generated uniformly at random. And this helps break the dependence of the secret with any set of n-1 values. And in this example, you can see that the operation I use is the XOR for a Boolean masking, but it can be any other operation. And so usually the theoretical security of masking schemes is proven under certain leakage models. And models vary in terms of convenience for security proofs and closeness to the reality of physical leakage. In the state of the art, the most widely used one is the probing model, where we consider that key variables of an algorithm leak during an execution. But to better approach the reality of physical leakage, the community have been trying to establish security in other models. Now, our work focuses on the random probing model, since there is a tight reduction from this model to the noisy leakage model, and it's still easier to prove. And actually, not a lot of work have tried to reason in the random probing model. So we formalize an algorithm as a circuit, which is a directed graph with variables as edges and operation gates as vertices. And in the random probing model, each variable leaks independently with a certain probability p, except for the output variable. And such a circuit is said to be random probing secure if any set of intermediate variables is independent of the secret input. A failure probability epsilon is associated with this security, which determines the sets that reveal information about the secret. And for this, we provide a formal verification tool that we like to call wraps, which given any small circuit computes the parameter epsilon as a function of p, for which the circuit is p epsilon random probing secure. And next, we provide a new notion of composition, which allows us to compose small circuits, or what we call gadgets, into a global random probing secure circuit. Now, in a nutshell, if we have gadgets for each of the basic gate operations that are random probing composable for certain parameters p and epsilon, we show that using them to construct a circuit, a big circuit, results in a global random probing secure one for parameters p and epsilon times the size of the original circuit and the number of its gates. And in addition to composing gadgets for global random probing security, we exhibit an expansion strategy inspired from work from 2018, which allows base n-share gadgets to be expanded and achieve arbitrary security levels. So the idea is to start from a base circuit with base gates and replace each wire by n wires carrying a sharing of the original wire. And so each gate will also be replaced by the corresponding gadget. And this strategy allows to replace the leakage probability P by a certain failure event probability, which is a function of P. And this can be applied recursively on the resulting circuit, reducing the failure probability until we reach a certain security level amplified to the kth level, which we call the amplification level. And we show in our work that to execute this, the gadgets should be random probing expandable. And if that's the case, then the resulting expanded circuit will also be random probing secure with a failure probability to the power k, the expansion level. And after this, we are able to instantiate the expansion strategy with a 3-share gadgets construction that we show are random probing expandable using our verification tool graphs. And we show that they can tolerate a leakage probability of about 2 to the minus 8 with an asymptotic complexity in kappa to the power of 7.5. Kappa is the security parameter. In comparison, we exhibit the instantiation provided in the original work from 2018, which tolerates a much lower probability of about 2 to the minus 25 with an asymptotic complexity that is close to ours. So the takeaway from our work is the introduction of a new formal verification tool for security of any small circuit or gadget in the random probing model. We also introduced new notions of composition and expansion for achieving global random probing security levels by using small secure base gadgets. And finally, we instantiate this notion with a concrete construction that we show using our tool tolerates a probability or leakage probability of about 2 to the minus 8 with a complexity in terms of the size of the circuit C and the security parameter to the 7.5. Thank you very much.
Thank you, Anand. Thank you for the talk. Do we have questions from the audience or comments?
So no questions so far. Let me check the Zulip chat. Again, just a reminder, you can post your questions here on Zoom, but you can also post them on the Zulip chat because that way it's persistent and people can answer questions after the Zoom session is over. So if there are no questions, I had a quick question. I don't think you mentioned this in the talk, but it's in the paper. I noticed that there is a p to the 3/2 parameter in one of the expressions where you're trying to basically, I think, tie down epsilon and the probability of a random failure. I was just curious if you had any intuition around that sort of 3/2 exponent.
Oh, in the instantiation, you mean of our construction?
Mm-hmm.
Yeah, because actually the 3/2 comes mostly from the failure function of the multiplication gadget, because if you can see in our paper for the epsilon in the random probing expandability property, you have a failure that is independent for each of the inputs, and you have failure that is on the input. And the global failure of the multiplication gadgets will be the maximum between the failure on each of the inputs independently and the square root of the failure on both inputs. And so the function that is computed by our tool for the multiplication gadgets had a power of 3 actually, but this power of 3 was a failure on both inputs 1 and 2. And so taking its square root, the final function will have the power 3/2.
That's very useful. Thank you.
You're welcome.
Maybe a quick question also from my side. So you didn't talk much about performance issues in this short talk, but I remember some things from the paper. So especially the new construction. So mostly with respect to randomness, how practical do you think this new construction is kind of for real world applications?
So we show in our paper that with our instantiation, when expanded it to achieve a certain security level, the more we expand it, the more costly it will be. But it should be noted also that the construction that we provide is a concrete example of just to show how the expansion strategy works. But there are more constructions that are more optimal in terms of complexity and in terms of tolerated leakage probability also. So maybe our instantiation to achieve a high security level is not very well adapted, But we have found other constructions that have a higher amplification order, for example, and so they don't need a high level of expansion. So they should be more practical to use. So it's actually an open problem to find the best instantiation.
Okay, thank you. Yeah, I guess we're good to go further. Thanks again.
So just before we move to the next speaker later, there's one more question on the Zulip chat that I just want to call attention. Abdul, you can respond to them privately. I mean, you can respond to them in the Zulip chat.
Sure.
Okay, thank you very much.
Okay, so maybe we move on. FX, can you share the slides? Yes, so great. Our next speaker is François-Xavier Standard. Again, a big group of co-authors. So I only mention the speaker, so you can all read that. And he also see in the paper. So the talk is mode level versus implementation level, physical security in symmetric crypto, a practical guide through the leakage resistance jungle. FX, go ahead.
Thank you. So I will also try to summarize the results we have. And for motivation or introduction, I will start with the NIST lightweight crypto competition. So at the moment, the NIST is trying to standardize new authenticated encryption schemes with hopefully good features for lightweight implementations and side channel resistance. And therefore, we have many candidates designed with leakage in mind. Sometimes it's working at the primitive level, like typically we have block ciphers and permutations that try to minimize the number of nonlinear components. Sometimes it's working at the mode level, and then it's using different design tweaks. So as typical examples, one thing that is popular is playing with ephemeral key evolution. So there you generate a fresh key and you make the key evolve through the computation in order to improve confidentiality with leakage. Something else that is used is using key generation functions and tag generation functions that are strengthened against side channel attacks, both for integrity and confidentiality. And for example, sometimes we also use two-pass designs in order to better cope with decryption leakage. So all these, and there are others, in fact, all these are intuitively appealing ideas. And maybe one limitation is that the constructions rarely come with explicit specifications of the guarantees they provide and the physical assumptions they require, which makes things a little bit difficult to compare. And the goal of this paper is really to try using the leakage resistance literature in order to clarify a little bit this state of the art. So for this, we are going to use authenticated encryption schemes that we split in 4 parts, as I already said. So the first part is the key generation function, which is optional. Then you have the bulk computation, which processes the message blocks. Then the tag generation function, and finally the verification. In the formal part of the work, what we do, which is as usual, is trying to reduce the security of the mode to some combination of physical and mathematical assumptions. And there, one problem that we have is that you have many competing physical assumptions in the literature, most of them coming with pros and cons, no complete agreement on what to use. And most of the times for current analysis, people combine several assumptions in order to try gaining insights about the security of the schemes. So this also makes things a little bit difficult to compare. And in this respect, a first observation in the paper is that if you try to translate all these assumptions into necessary design goals, you can really simplify them into 2 main security conditions that we call DPA security and SPA security. So these are 2 types of attacks that would be analyzed by evaluation labs nowadays. So DPA security means that we need to prevent attacks where the adversary can observe the leakage of the primitive for several inputs or many different inputs. And SPA security is the same, but the adversary can only observe the leakage of a few inputs. And typically, DPA security will be to protect long-term secrets, and SPA security is more related to ephemeral secrets. And interestingly, as put in the table, At the bottom of the table, for integrity guarantees, we can sometimes even tolerate unbounded leakage, which means that for some part of the implementation, we can give absolutely everything to the adversary. So to try giving some intuition about why using weaker physical assumptions is very relevant in practice, this table summarizes or gives some approximate numbers for the performance overheads that you will need for DPA security and SPA security. And the summary is that DPA security is very expensive. The overheads can be by a factor 100 or more. SPA security, let's say it's moderately expensive, so factor 1 to 5. And of course, when you tolerate unbounded leakage, you can use the implementation as is, and then it is very efficient. So that's one thing. The second thing that we try to simplify in the paper is the definitional framework that we have in leakage resistance, because currently in the literature, you have many possible security targets. So this is somehow, to some extent, unavoidable, because in this physical world, the use of composite definitions where you separate confidentiality and integrity this use is interesting, because what you need physically to guarantee confidentiality and integrity can be very different. And for example, tolerating unbounded leakage, you can only do that with integrity guarantees. So we keep that, but we still try to organize all these definitions in a more limited fashion with different grades. And essentially, for confidentiality, we will use CCA security. For integrity, ciphertext integrity. For leakage, we consider leakage in encryption only. This is the L1 notation, and leakage in encryption and decryption. This is the L2 notation. And we additionally consider some kind of misuse, which comes with some technicalities that I leave for the long version of the talk or the paper. And based on all that, the type of results that we have is summarized in this table. So the idea is that we can take different authenticated encryption schemes. Here, I give the example with 6. All of them are split in different parts, right? Key generation, message processing, verification, and so on. And we have the different security targets for confidentiality and for integrity. And the table essentially tells hardware engineers what they have to satisfy. So if I take one example, example, OCB is a mode of operation that doesn't come with any leakage resistance guarantee. So there, you will really ask hardware engineer to guarantee, to ensure DPA security for all the parts of the implementation. And at the other extreme, if I take TEDT, this is a mode with strong leakage resistance guarantees, but of course it's also more expensive. In this case, you still need DPA security for the key generation function and the tag generation function, but all the rest has weaker requirements. So for confidentiality, everything is essentially SPA security, and for integrity, you can leak unbounded for all the rest of the implementation. And what's interesting here is that you can really, it motivates this idea of leveled implementations where you have different parts of an implementation that have different levels of security against side channel attacks, and therefore different performance levels. So quickly, the conclusion, I would say from the theory point of view, the main conclusion or take-home message is that in the field of leakage resilience, there's no single right definition of authenticated encryption. You more have a kind of continuous trade-off between mode level and implementation level leakage resistance. And in practice, I would say the main conclusion is that as the security level that you want in practice increases, then of course leveraging mode level guarantees is going to gain interest and can really lead to significant performance gains, because all the countermeasures are actually very expensive in this field. And that's it. Thank you.
Thank you. Thanks, FX. So let me check with my co-chair, session co-chair. No questions from the audience?
No questions yet.
Okay, so maybe a quick question. So you were talking about the overhead in the range of factor 5 to 100. Yeah, for DPA protection, basically. So could you share some insight about what do you expect to be like requiring factor of 100 in terms of protection, and why? Does it relate to specific design with candidates or you know, security requirements? So
Yeah.
Where does
So
where would that go?
these are figures that I take from the masking literature, right? So it's ISW like masking with larger number of shares as you would typically need in software implementations if you want to reach high security levels. So we are also speaking about attacks that can cope with 2 to the 40 measurements typically. So that would require more than 8 shares.
And when
I
you
guess
say higher,
security.
And when you say higher order, you mean then which order typically?
As I said, for this software platform that we like ARM Cortex type of things, it's more than 8 shares. It's 8, 9, 10 shares if you want this security level. And between 4 and 8 shares, you already have some security, right? You can tolerate 100,000 measurements, 1 million, something like that.
Yes, but practically speaking, do we need that high order security?
It like 1 million, 10 million measurements, it's not something that take days to compute. So that's really something to decide depending on the application.
Yeah.
These are also figures. We just had this workshop with the NIST about standardization of masking schemes, and it was more or less agreed that between 4 to 8 shares in software was relevant, and probably in hardware it would be a bit less because you have more noise and stronger possibilities to combine with other countermeasures.
Yeah, sure. There is a big distinction there. Okay, thanks. Is there a question in the meantime? People need some coffee, I guess, to wake up a bit. Okay. Yeah, let's thank the speaker and maybe proceed to the next talk. Thanks again. Next speaker, could you please share your screen with us? Yes, it's coming.
Yep. Can you hear me?
Yes, great. So next talk is on leakage resilient key exchange and two-seed extractors, and Willy Quash will give the talk. Go ahead.
Yeah, thanks for the introduction. So as the title suggests, in this paper we study leakage resilience for key exchange, and this is joint work with Sinli, Farmima, and Daniel Wicks. Oops, that's internet. Okay. So what we are considering in this paper is key exchange, where you have two parties, Alice and Bob, who execute some randomized protocol, and in the end they manage to agree on a shared key. So to be more precise, what I'm considering here is what I'll call a NIKE key, which is a non-interactive key exchange, where Alice and Bob can compute their messages in advance before the protocol execution, and that is secure against passive adversaries. So we require that if there's an eavesdropper that can see the messages that are exchanged during the protocol execution, then she shouldn't be able to infer any information about the keys. Yeah. So on top of that, we'll consider another layer of security, so leakage resilience. And the basic question that it asks is what happens if the random coins that Alice and Bob use to execute the protocol is unreliable somehow. So for instance, Eve could get some information on Alice and Bob's random coins through some trapdoors, and would like to ensure that even if this is the case, the protocol is secure. So the way we'll model that is that Eve will be able to see Alice's random coins that she uses for the protocol execution, compress that information down somehow, and keep some leakage in her head, do the same for Bob, and require that in the eyes of Eve, the true keys, the keys that is shared in the end of the protocol looks uniform. So it turns out that this problem has been quite heavily studied before. In particular, there are kind of generic techniques, and actually all the techniques that I know use some kind of leak-free randomness. So what does it mean? You can, given an key, you can kind of generally transform the protocol by requiring Alice and Bob to use some additional randomness, here denoted in green, such that if Eve doesn't get any leakage on those green random coins, then the protocol remains secure. So, but leak-free randomness is really not something we would want in practice, and actually goes kind of against the main motivations of leakage resilience. So one main goal of the paper is to actually get pure key exchange scheme. And we notice, just for notation, I'll call a leakage resilient key exchange. Key exchange that remains secure whenever Eve gets some leakage on Alice and Bob's random coins. In this setting, something that to notice is that it actually makes sense to consider a symmetric version of this protocol. So where Alice and Bob would start with a secret key and would in the end agree on the new uniform key. So here, leakage resilient means that Eve should be able to leak jointly on the secret key on Alice's random coins. So in some sense, imagine she has a backdoor to Alice's device and get like all kind of information she wants. So so how could such a primitive be useful? So for instance, if Alice and Bob share a key, this key gets somehow leaked, and they would like to refresh that key. So that could be an example application. And the question you may ask is, why would you consider such a setting? You can just use standard leakage resilient key to do that. And the point here is that it's a simpler problem, and you could hope for better solutions. So here, what we're aiming for is information theory constructions. Yeah. So now I can describe our contributions. So our first contribution relates to this symmetric setting that I just talked about. And we show that this symmetric key leakage resilient keys is very related to a notion of randomness extractor that we call true seed extractors. So true seed link, that pretty much corresponds to the special kind of symmetric key key, where Alice and Bob just send to each other their whole random codes. So what happens is that the protocol that they use to derive the key in the end is, in some sense, extracting entropy, fresh entropy, out of some source, here the key that they share, using some seeds, the random coins that they use for the protocol. And that's pretty much what a true seed extractor would be. Then we show how to construct such true seed extractors, given some communication complexity lower bounds, more precisely in the number on forehead model. And because we have efficient functions that have high communication complexity, in the end, what we obtain is information theoretic constructions of such symmetric key keys, leakage resilient. So our second set of contributions would be in the more standard public key setting, where Alice and Bob do not share a key in advance. And somewhat surprisingly, I'm personally not aware of any construction in the setting. And one potential reason why is the following impossibility result we show that rules out any black box reduction from any cryptographic game for a special kind of leakage resilient keys, namely those with perfect correctness and with not too small leakage. Yeah, so just to parse this, what I mean by cryptographic game, I refer to the talk for more details, but that essentially includes all the assumptions we like to make usually. But still, there are some limitations to this black box impossibility result. And so we would still like to get some constructions. And at least in the theorem statement, as I stated, there are some ways, potential ways to circumvent it. Indeed, for instance, if we consider leakage resilient keys with small leakage, we show that any key is actually natively resilient to log size leakage. So we leave the question of constructing keys with non-black box reductions, or that would somehow meaningfully use the fact that they have statistical correctness instead of perfect correctness as a natural open questions. And last, if you dig a tiny bit more into the impossibility results, we can notice that it actually only deals with keys in the plain model, or at least using some kind of public coin setting. So it turns out that if you're okay using secret coin settings, we can actually give instantiations. So for instance, we managed to get an instantiation using parents. Yeah, that's pretty much all I had to say. Feel free to ask questions, and thanks for your time.
Thanks for the talk. Let's see if yes, there is a question. Anand, you want to take over? There is a question
Sure.
in Zoom chat.
So Radeep, if you want to unmute yourself and ask the question, you can do that.
Thanks. So I wanted to ask that leakage resilient Nike in the public key setting, isn't it trivially impossible? So for example, the adversary can just embed the session key derivation function while leaking on the secret key of Alice and just leak directly from the Nike key.
So you mean that the leakage could be like somehow like directly related to the N key?
Yes. So for example, when the leakage can be as follows. So the adversary wants to leak on the secret key of Alice. So it takes the public key of Bob, and the leakage function is just the Nike shared key derivation function. And this directly gives you say some bits of leakage on the Nike key, which which breaks the security.
Good question. So the thing is that the leakage should be computed before seeing the transcript of the protocol. Otherwise, indeed, it doesn't make sense. And for the same reason, we asked that the leakage should be kind of independent between, should not be a joint leakage on Alice and Bob states. It should be like independent on Alice and then independent of Bob. Otherwise, you can just compute the key and leak the key. So in some sense, the leakage has to be like kind of independent of what's happening in the protocol execution. So it's like more leakage that you get in advance beforehand, and then you execute the protocol and then secure.
Okay, so so does that mean that your protocol is only secure in the split state leakage model?
Yeah, kind of. I mean, otherwise it doesn't make sense. The problem doesn't make sense if I understand correctly.
Okay, I see.
Thank you, Supradeep. And again, I encourage others to post questions on the Zulip chat so that you can continue the discussion. Maybe if you want to repost it, that would be great. I guess we're out of time, so we'll move to the next stop.
Yeah, we should move to the next. We're halfway through this session, which seems to be good timing if we proceed to that. So could you please share your slides? Our next speaker is Kevin Yeo.
Can you see the slides?
Yes, we see the slides. And his talk is on lower bounds for encrypted multi-maps and searchable encryption in the leakage cell probe model. And it's joint work, with a few more people. Please go ahead, sorry.
Sorry, I interrupted you. Thank you for that introduction. Yeah, like you said, this is a joint work with Sarva Patel and Pino Persiano from the University of Salerno in Google. All right, so the problem that we're considering in this paper is sort of the idea of outsourcing storage, essentially. You can sort of have a data owner or a client on your left that wants to outsource, let's say, some sort of map on to a potentially untrusted server on the right, let's say like keys and values. And sort of if you do this in a naive way where, even if you just did sort of plain client-side encryption, what happens is when the data owner wants to sort of retrieve a key and the associated value for a key, the server sort of sees what keys were being queried over time. And this is sort of, you can imagine that over a long period of time, the server will be able to get more detailed information or statistics about what's going on or what the intent of the owner is or what the underlying data is. So in this work, what we're really considering is a problem where essentially we want to provide privacy for the requested key. So for example, the data owner has outsourced this data in some fancy way. It does a request for key KI, receives the value VI, and the server has, the server doesn't know exactly what the key KI is. And I'll be more formal on what the privacy actually means, but sort of we're just trying to hide what key is being queried. So it turns out that, what I'm considering essentially are maps or multi-maps. And there's actually been a lot of work on this data structure over the years. And you can actually view this sort of as a privacy spectrum. So on the left, you have sort of the most efficient but least private sort of solutions, and on the right, you can have the least efficient but the most private solutions. So I mean, the most efficient solutions are obviously the ones that provide no privacy. So you can think of plain text maps, such as the FKS hashing, the very famous ones from the 80s, that give you essentially constant efficiency but leak everything because the goal was not privacy. So in recent years, there's been a step up where people have considered the idea of structured encryption, also known as encrypted search, where the efficiency essentially is order 1. But the leakage is something which is something non-trivial. It's a non-trivial leakage function, and I'll get back to, and I'll explain in more detail just a little bit later. And finally, on the far right, what we have essentially are oblivious RAMs, where you get, where you have essentially optimal privacy. The only leakage essentially that's leaked is the length or the number of operations that are performed, but the efficiency jumps logarithmically higher from constant to log n. So in this work, what we're actually trying to explore is this area between structured encryption and oblivious RAM. Essentially, we're asking, we have this sort of, we know that the left, there exists constant constructions with non-trivial leakage, and there exists log n constructions with almost no leakage. How does this ramp up? Where does this go from constant to log n? What privacy is required, or what privacy can we actually obtain with constant overhead that's maybe better than the non-trivial leakage functions that we currently have? So, okay, like I said, if I want to explore this, I sort of explain to you what is structured encryption and what this non-trivial leakage function is. So it turns out that this whole area of structured encryption, a lot of the ideas can actually be formulated in a very simple idea of a hashing encrypt compiler. So what we do is you consider any plaintext map with operations like insert, get, and delete, and this is all done in plaintext. And what you do is you take the client or the data owner will keep some single private key, K, and simply hash all the keys Ki using some PRF, for example, and in CPA encrypt all the values. So if you do this, it turns out you can still do all the queries. For example, if you want to do a query, you just send a hash of your key that you're requesting, and you'll get back the encrypted value, which you can decrypt. And similarly, you can also insert. For example, if I want to insert a key Ki and a value Vi, I send the hash of the key and encryption of the value, and then the server and I tell the server to essentially insert these values, and the server would essentially insert it into the plaintext map. So I mean, this is a very straightforward. I mean, you can argue what kind of privacy it gets. This is a good question. So, okay, so yeah, insert. So let's explore it. So to take a closer look, what actually happens in the leakage, you can sort of see that for each query, the server gets to see sort of 3 pieces of information: the type of operation that's performed, a hash of the key that's being operated on, and an encryption of the value that's being inserted, or the encryption of values that are being returned for a query. So just to summarize quickly, that's these three operations essentially. Type of operation performed, the length of the query response, and the last thing which I really want to focus on is the key equality pattern. So what is key equality pattern? Essentially means that the server can see whether any 2 operations are performed on the same key or not. And this is simply because we're releasing a PRF, which is a deterministic value of the key of the requested key. So even though the server doesn't know, for example, the 2nd and 3rd operation are being performed on dog, it knows this is the same value. And it also knows, for example, the 3rd and 4th operations are not for the same key because their hashes are different. So, this you might ask, okay, this seems like a very weak notion, or it might not. It's not very interesting as a construction. But it turns out that this leakage essentially matches all the best constant construction schemes for structured encryption and encrypted search. All right, so I mean, this seems like an inherent bottleneck, and it's something that we're trying to explore here. So, a natural question is, can we do better? And the answer is, well, looking at the 3 leakage functions, it turns out there's only one that we can really work on. For the type of operation performed, it's actually not hard to mitigate. You can just repeat all operations. There's only a constant number of operations. You can do some dummies, and you can actually probably mitigate this without any overhead. The length of the query response is actually much harder to do without increasing cost significantly, obviously, because if your map is inherently has one key with a very long value, or a multi-map with a very long value, you probably can't mitigate this. There's some work that does this actually, but it's actually very hard to mitigate just naturally because of the problem. So we focus on the 3rd, which is the key equality pattern. And we said, okay, so we know what the key equality pattern is. What we consider is something just slightly worse, or slightly better in terms of privacy. It might not even be meaningful, but let's try it. And we call it decoupled key equality. So what we're essentially saying is we want to decouple key equality between operations. So before, in the previous slide, what I had was the cats were all colored by the same sort of color purple. In this case, what I'm okay with the server learning whether the same key is being operated on for 2 insert operations, but between an insert and query operation, I would like to sort of decouple the knowledge. So for example, the 4th and 5th operation, even though they're performed on the same keyword cat, I wouldn't like the server to know that information. But I'm okay with the server learning whether 2 inserts are for the same cat or not, like let's say the 1st and 4th operation. And you can do the same thing with the other sort of keyword dog. You see that since one's an insert and one's a query, we would like to sort of decouple them and say the server shouldn't learn whether they're for the same requested key or not. So you can ask, is this really a meaningful privacy guarantee? I don't know. But what we actually proved is something quite surprising, which is the following. And this is the main result of our paper. Essentially, it's sort of that any encrypted multi-map with leakage, at most the decoupled key equality pattern must have omega login overhead. So essentially what it essentially means is if you want just the key equality pattern, you're okay. You can get constant overhead with the hash and encrypt compiler, which you described earlier. But as soon as you decouple, as soon as you want this very, very slightly stronger notion of privacy, which might not even be meaningful, you end up having this jump to logarithmic overhead. And of course, this is tight because there exists logarithmic ORAN-based encrypted multi-maps that leak much less than the decoupled key equality pattern. In fact, they leak just the number of operations. So going back to the privacy spectrum in this paper, what we prove essentially is sort of that this ramp, essentially, wherever structured encryption currently is at. Yep.
Sorry, Kevin, could you wrap up, please? We're running out of time.
Slide, yeah. So whatever we're at, this is the last. This is essentially what the best we can achieve. And everything beyond that is thank you.
Thank you. Thank you for the talk. So like I said, we're a bit running out of time, and you went a bit on after 5 minutes. So I'd like to redirect the questions to Zulip. There must be questions. Yeah, thanks for the talk, Kevin. And yeah, hope people will follow up with questions there. We're moving on to the next talk in this session, which will be given by Gareth. I'm waiting for your slides to be shared. Yes, great. So Gareth will speak about fast and secure updatable encryption. That's also collaboration with other people that he may choose to mention or not. Please go ahead.
Gareth, you're probably muted.
Yes, Gareth, we don't hear you.
Okay, try again. Okay, can you see the slides? And
yes, yes, both.
Okay,
go
thank
ahead.
you. Sorry about that. Okay, so yep, this is joint work with my former colleagues from NCNU in the beautiful city of Trondheim. So this talk concerns secure data outsourcing, where a client encrypts files to send to some untrusted storage provider. And key compromise, which can happen from a device being lost or stolen, a security incident, insecure hardware. This would give decryption capability to an adversary that is in possession of the ciphertexts. So to mitigate against the risks, users can rotate their key to a fresh key, either periodically or on demand. However, downloading and re-encrypting all files is simply not an option in the vast majority of use cases for outsourced and encrypted file storage. So to get around this problem, updatable encryption was introduced by Bernay et al. In 2013. The user calculates an update token from their old and their new key and sends this token to the server. The server then applies this token to the old ciphertext to produce a new ciphertext. The subscript here indicates the time period or the epoch. So once this process is complete, the server can delete the token and the old ciphertext, and the user can delete their old key and their token. So ciphertexts, tokens, and the update process should, of course, not reveal anything to the server about the underlying plaintext. And I should say here that updatable encryption comes in two flavors. Ciphertext independent schemes have the same key for all ciphertexts, which means you only need one token. We'll be focusing on this for the talk and the paper. Ciphertext dependent schemes have one key per ciphertext, and so one token per ciphertext. Okay, so prior work by Lehmann and Tuckman has defined confidentiality in a very strong corruption model that allows the adversary dynamic access to keys, tokens, and ciphertexts across different epochs. And the challenger tracks and essentially works out if a trivial win has occurred at the end. So the first stage is to assess confidentiality of fresh ciphertexts called int-enc. The challenge phase is very similar to the regular indistinguishability game for encryption. The second stage is to assess updates by int-upt, in which an adversary submits two ciphertexts that existed in the prior epoch, receives an encryption of one of them, and must decide which one was updated. So if the adversary had access to this crucial token here for the epoch delta e tilde, then a scheme can only be secure if its update procedure is randomized. This can occur perhaps in the Elgamal-based RISE scheme of Lehmann and Tuckman. And in our work, we actually distinguish these definitions for randomized updates and deterministic updates. Ciphertext integrity has also been previously considered in the expected way, but in this strong corruption model. So we define a new security definition for updatable encryption. We call this INUE, where an adversary submits a message and a ciphertext from the prior epoch and receives back either an encryption of the challenge input message or an update of the challenge input ciphertext. And as it turns out, this definition is actually strictly stronger than the combination of the two prior confidentiality notions. So please see the talk of the paper for full details, but we show how our notion relates to prior work in the randomized updates case, also the deterministic updates case, and in the chosen ciphertext setting. So we also show the expected composition result, and we do so for each of these confidentiality definitions. So additionally, we give a new updatable encryption scheme that we call SHINE. The encryption procedure takes a nonce and a message, passes that value through a permutation pi, and exponentiates the outcome. Decryption works exactly as you would expect. So the update procedure produces a token by multiplying the new key by the inverse of the old key, and the server simply exponentiates ciphertexts by this group element. Note that this procedure is deterministic. So the internal permutation output is static, so decryption is again straightforward. In the paper, we actually define 3 different variants for different size messages and show how to provide ciphertext integrity. We also discuss a number of options for instantiating our schemes with like different block ciphers and also different elliptic curve groups, and also for mapping in between these spaces as is necessary. So our schemes are secure under DDH and CDH in the ideal cipher model. And the composition result that I mentioned earlier tells us that our schemes are CCA secure. Here we mentioned some prior work and the maximal security properties that the schemes can achieve. And our suite of schemes achieves the best known security level for updatable encryption with deterministic updates. So efficiency very much depends on the sizes of the messages being encrypted. So please see the paper for a more thorough comparison of efficiency and also security. So at the CPA level and the CCA level for short and long messages, our schemes are at least as fast as prior work. Okay, so to wrap up, we give a new security definition for updatable encryption schemes. We show the expected composition result. We give a new suite of updatable encryption schemes that meet the strongest possible known security definitions. From a technical point of view, we also advance the capabilities of some existing proof techniques, in particular this epoch separation strategy that's been used in prior work. Thanks very much for listening, and please check out the extended talk for many more details.
Thanks, Gareth. Let's move to questions from the audience.
So there's there's one question. It's a short question, so I'm just going to read it out. Pratik Sarkar asks, what is debt in deterministics in debt CCA?
So this means that so this is from the perspective of the security definition, but it's basically to cover schemes for which the update procedure, this exponentiation by the token, for example, is deterministic. So you do not need to generate randomness to update the ciphertext. And remember, it's the server that's doing this updating.
For that, actually, I had a question on the slide. While we wait for more questions, we have a couple of minutes. So the permutation, which is, I guess, modeled as an ideal permutation, is that public in the scheme, or is that part of the private key, basically?
No, this is public. So in the paper, I think we mention the possibility of using AES with, let's say, normal size but large blocks, say 512 bits, with a key of all zeros. So this would be absolutely fine as far as our construction is concerned, because the nonce is the thing that provides the randomness in the initial encryption. So the ideal cipher here essentially models the inability of an adversary to gather any information by doing anything other than actually managing to get this decryption key. It makes the proof a lot easier.
And is the white block, is that a problem for schemes in the sense that?
So it does create some challenges with mapping to, for example, elliptic curve groups, but it's certainly possible. You just need to be a bit careful with mapping to the correct group. And there's a discussion of this in the paper, which is perhaps more conclusive than what I can try and put across here.
Cool. I see there are no other questions on Zulip or on the chat, but again, feel free to add questions in the Zulip session, and that way we can continue discussion. So I think with that, we can move on to the next talk later.
Yes.
And thank you, Gareth.
Yeah. Thanks again, Gareth. And the last talk in this session will be given by Daniel Wicks. It's the talk on incompressible encodings, and it's a joint work with Tal Moran. Daniel, go ahead.
Great, thank you. All right, so let me start with a question. And the question is, how much space does it take to store Wikipedia? So it turns out you can actually download a copy of Wikipedia for offline use, and some reasonable version of it is about 50 gigabytes in length. So it's quite large, as you'd expect. But there's another way to store Wikipedia, which is you just store the link, www.wikipedia.org. That only takes 17 bytes. And as long as you have an internet connection, using this link, you can access the Wikipedia data whenever you want. So it's sort of as good as storing the Wikipedia data. And the point I want to make is that when we consider some public data like Wikipedia, even if the data is very large, because it's public, it's trivial to compress it. Just store the link for it. And so the main question or goal for this talk is to come up with some sort of an incompressible representation of public data. In other words, I want to have some representation of Wikipedia that requires the full 50 gigabytes to store, even for someone that has the link to the underlying Wikipedia data and can access that for free. So that's the notion of incompressible encodings, and let me actually define it. So it just consists of two algorithms, an encoding and a decoding algorithm. These are keyless public algorithms. Anyone can run them. There's no secret keys. The encoding algorithm is a probabilistic algorithm. It takes some data M as an input, and it encodes it into a code word C. And you can think of this code word as some sort of a randomized representation of the underlying data. Anybody can come and decode the code word and recover the original data. So it's having the code word is as good as having the underlying data. And we want correctness. So if you encode and then decode, you get back the original message. And we want incompressibility, which considers an attacker that knows the underlying data. So the attacker has the link for Wikipedia. He knows Wikipedia for free, but his goal is to compress this code word, this randomized representation of Wikipedia that we created. So the attacker consists of two algorithms, compression and decompression. The compression gets the code word, tries to compress it down into some smaller value W. And then later the attacker wants to take W and decompress it to recover the code word. And the security requirement says that no efficient adversary should be able to succeed in this game, should be able to succeed in compressing code word with better than negligible probability. So we have two parameters here. There's the code word size alpha. And here we want the code word size alpha to not be too much bigger than the data size. So the encoding should not add much overhead. And then there's the parameter beta, which is how much adversary is allowed to compress to. And we want that to be also essentially as big as the entire data size or code word size, which says that the adversary needs to store essentially the entire code word in order to be later able to decompress it and recover it. So it turns out that this notion was introduced in a prior work from crypto last year by Damgard, Ganesh, and Orlandi. And they defined a slight variant of these incompressible encodings. They had a different name for it. But they thought of it as a tool for building a larger cryptographic primitive called proofs of replicated storage. And I'm not going to talk about what those are. But in that context, they gave a construction of these incompressible encoding, albeit with several major caveats. So one of the caveats is that the construction required some ideal permutation or random oracle model. The encoding time was also quadratic. And here we want to apply this to very large data, like many gigabytes or terabytes in length. And so quadratic time is really impractical. And lastly, it turns out that the proof of security they had was flawed or somewhat incomplete. It didn't work for fully general attackers. And this was actually also observed by concurrent work to ours by Gargle and Waters. And they managed to actually give a fixed version of this proof. So prove that the original scheme from that work is secure. It required quite a bit of an effort, and it's a complicated and subtle proof. So in our work, we essentially initiated the study of these incompressible encodings as a standalone primitive that is sort of interest in its own right. And we give new and improved construction. So we show a construction that works in just the common reference string or random string model without random oracles. The encoding time is linear. And lastly, our proof is fairly simple. So it's a different construction with a much simpler proof. We also give some lower bounds and negative results, for example, showing that the common reference string model is necessary. You can't do it in the plain model, at least under black box reductions. And we also give a new application to big key cryptography. So let me mention a little bit about this application. This is motivated by computers becoming compromised, remote attacker hacking into a computer. And if you have a small cryptographic key on your computer, that's the first thing the attacker is going to steal or going to exfiltrate. It's very valuable. And the idea to prevent against that is let's make our secret keys big, like many gigabytes or terabytes. And the idea is big keys should be harder to exfiltrate, maybe because you have some firewall that detects such large leakage. And so there's actually been a lot of work on this idea called big key crypto systems or bounded retrieval model. But one thing common to all these works is that they require the user to waste a lot of their storage on storing this long secret key, many gigabytes or terabytes long key, which is useless for any other purpose other than to do crypto. And so the idea in our work is let's make the key useful. Let's make it store some information the user would want to store anyway, maybe Wikipedia or their movie collection, etc. So is Wikipedia a good secret key? Well, obviously no, Wikipedia is public. Everyone has it on the internet. It's a terrible idea to use Wikipedia as your secret key. But the idea is to use an incompressible encoding of Wikipedia. And this makes sense because we showed that incompressible encoding cannot be compressed. If an adversary wanted to exfiltrate this incompressible encoding, he would have to essentially exfiltrate the entire size of the data. So a lot of information. And so we construct public key encryption in the setting where the secret key can be an incompressible encoding of some useful data like Wikipedia or a movie collection, and the adversary would need to exfiltrate almost the entire key to break security. So in the last minute or so, let me just give a very brief and simplified version of our construction of these incompressible encodings. And here I'm going to assume we have something called a lossy trapdoor permutation. So it's a lossy trapdoor function, which is also a permutation. We don't quite have these, and in the paper we deal with that, but for the simplified view, let's just pretend we have them. And so to encode the message, I'm just going to pick a public key of this permutation, and I'm going to use along with a trapdoor, and use the trapdoor to invert this permutation on the message XOR with a common random string. So and this X, the inverse I get, is going to be part of the code word. And so you can easily decode this by computing the permutation in the forward direction. And the secure proof really considers just two steps. The first step is, let me just switch the distribution and of the code word and think of choosing it by choosing X to be random and programming the common random string, the CRS, to be f of X XOR with the message. So this is exactly the same distribution, nothing changed. But then in the second step, now I'm not using the trapdoor anywhere, and I can switch the public key to lossy. Which means that FPK of X loses much of the information about X. And in this case, once I do that, then because FPK of X doesn't reveal much information about X, the X part of the code word has a lot of real entropy, even given the CRS. And therefore, it cannot even information theoretically be compressed. And this shows that in the original distribution, it computationally cannot be compressed. Otherwise, the attacker could distinguish these cases. So that's the entire idea, and thank you.
Thanks, Daniel. Thanks for the talk. We have still a few minutes, maybe, if there is a short question. Yeah, there is a question. Anant, maybe moderate, please.
Sure. Yeah. I actually had a quick question, and then there's another one on the Zoom chat. So my quick question was, so you mentioned you can use incompressible encodings in this big key crypto. Are there any extra steps you need to take to sort of use the big key, or is it some standard kind of transformation I can plug and play sort of thing?
Yeah, absolutely. So I didn't mention a lot of that, but there are extra steps. So we need to build a specially designed public key encryption for this purpose. It's essentially public key encryption that ensures that the only way to break security is to have some sort of a version of the secret key. I can take an attacker, break security, and extract the secret key out of them. So any such attacker that would leak a small amount of info and break security would serve as a compression algorithm for the incompressible encoding.
So it's slightly related to the compressibility sort of definition, basically.
Yeah, I need
decryption.
I need them to work together.
That's useful. So Pradeep had a question. Maybe you can unmute yourself.
Hi, thanks for the talk, Daniel. So I wanted to ask that in the proof of security, you will need to program the CRS, right? So is it true that you can only prove selective security in this case?
Yeah, absolutely. Good point. So yeah, we only prove selective security, and we actually show that this is inherent, that you cannot prove adaptive security in the CRS model via black box reductions. So we also give an alternate construction where if you replace the CRS with a random oracle, then you can even get adaptive security.
Okay, thanks. Yeah.
Yeah, no more questions?
So there aren't any questions. Actually, there's one question from Yevgeny on a different talk. So maybe you can quickly ask that, Yevgeny, and then we can wrap up.
Well, very quickly, for updatable encryption, it's a very nice construction. What we recall there are standard model constructions of updatable encryptions. Do they achieve your level of security, or there is some inherent barrier?
Yeah, it's a really good question, and something that certainly I've thought about quite a lot. The real challenge here is that in this very strong corruption model, in order to provide non-challenge ciphertexts, this is in some sense like a commitment to the epoch key. So we really need some way of programming our challenge into our reduction. And I really don't know how to do this in these schemes where you have essentially exponentiation for encryption and updating. But I think this is really something that might be possible if maybe you have an assumption on the PRP security, but then this seems to just create a lot more problems in the proof than it actually solves. So I would really like to know the answer to this as well.
Thank you.
Okay. So yeah, wrapping up here, I guess. Let's thank all the speakers in this session. Thank you all for joining. Please continue on Zulip, and I guess, yeah. Next up is social hour anyway, so yeah.
Yes, and I believe Leo should say something, except now I realize I'm putting him on the spot because I haven't told him what to say. We are, Leo, if you want to chime in, because there will be a social hour.
I'll just chime in to say, we're going to use there's a link on the program that you can go to. We're going to use the app from Tuesday. And Sophia